Number 31. First question of the B1 section. These are the 20 multiple choice questions that, of course, are supposedly two-step or a little more difficult than the 1 through 30 that we did. But 31, which Lewis dot diagram represents an atom of nitrogen in the ground state? So ground state means that electrons are filling from the lower energy position first before they fill higher energies. Okay, and we should recognize that a ground state configuration, okay, for electron dot diagrams represent the valence electrons. So let's go to the reference table to know the electron configuration and the valence electrons for nitrogen. Let's do that now. So looking at our periodic table, we can see nitrogen right here in the middle, and its configuration is 2-5. Now, what does that mean, party people? That means that we're dealing with, okay, here's our nucleus, okay, and then we've got 2 electrons, all right, if you think about shells of electrons, in the first shell closer to the nucleus, and then we have the outermost electrons, or 5 electrons in the outer shell, and these are the ones that are higher energy, the ones closer that feel the positive force of the nucleus. Remember, electrons are negative, so negatives and positive attract, so the closer ones, okay, are lower energy. So it's the higher energy ones, the outermost electrons, in this case the valence electrons, that become the outermost electrons that we use for electron dot diagram. So it's the valence electrons, that 5 electrons. So the outermost electrons, the ones that have higher energy, represent how many dots. So if we're doing oxygen, I know that we're not, it would be 6 dots. Fluorine would be 7. Notice our noble gas has the 8. That makes them very stable. Having that octet means that we have a very stable, and they're ground state because electrons are going in order. So that's why they said that. If this was an excited state, maybe an electron would jump here, and that would be a 1 electron, and that would be 6, right? We've talked about going out of order, electrons getting energy to pull away. But in this case, they said ground state, so we're just looking for the valence electrons for the dots. So right from our reference table, nitrogen is 2-5. And so therefore I'm looking for an N with 5 dots, okay? And easy to see that choice 2 is going to be that answer. Now, something else with electron dot diagrams, we use them to show bonding, but sometimes they'll just ask you to do this in the part 2 section. They'll say, hey, what is electron dot diagram of an element? You draw the element symbol and the number of dots that represents the valence electrons, that outermost number. Something else you should be aware of, that this symbol N represents the core electrons. These are the electrons that are not in the filled energy level, and that would be the 2. And it also represents the nucleus, which is the protons and the neutrons. So understand that the symbol also represents the core electrons, or sometimes they call them the kernel, and the nucleus. Now, I drew 1 proton, 1 neutron. Obviously, atomic number for nitrogen is 7, so there'd be 7. Okay, but I'm just giving you a representational model there. Okay, so any case, it's just 5 dots. Choice 2 for number 31. On to 32. Number 32. The atomic masses and natural abundances of the 2 naturally occurring isotopes of silver are shown. So we're talking about isotopes. Iso means same. So in this case, we're talking about the same element, silver, but a different number of neutrons. See, silver is silver, okay, because it has the same number of protons, but it has a different number of neutrons. Since protons and neutrons have the same mass, you can see that silver's got 109 has what? 2 more neutrons. Okay, so this is called the weighted mass problem, right? And I can see in this question, sometimes I've seen this as a choice. What is, If you look up silver on the reference table, just to give you some background, if you have no idea how to do this, and I always assume that when I'm reviewing this. So let's go look at silver on the periodic table to show what is its average isotopic mass. You may not have heard that wording, but that's what it is. The mass written for the silver element or atoms have a decimal place that show an average of all the different types of isotopes. Again, the isotopes are a different number of neutrons for the same number of protons, or in this case, silver. Remember, silver is silver because it has a unique number of protons. Let's take a look just to get a feel for this. So taking a look at the periodic table, we can see this big, baddest, boldest number is the proton number, and that is 47, and that's what makes silver a silver atom. If they had 48, it'd be cadmium. If there was 46, it'd be palladium. So you need to know that what makes an atom different from other atoms, or an element different from other atoms, is that proton number. Now we should also know that's also the electron number. If you add up all the electrons, remember this is an electron arrangement of a ground state silver, okay, it would add up to 47 as well because all the positives equal the negatives. But what I'm after here right now is the mass number. This is the mass number. It's got a decimal place. I told you that protons and neutrons have about the same mass, and that mass is called 1 unit or 1 atomic mass unit. It's a relative number. We can't put a scale on it. Why does it have a decimal place? It has a decimal place because they averaged all of the natural occurring isotopes for silver. And the reason why it's 107.868 is that the most stable and highest abundance isotope for silver must be 108, because this averages out to 108, because one isotope of the group, okay, is in greatest abundances. And what they do to get this number is they average all of the different forms of silver, all of the different number of ways it can have extra or less neutrons. That's an isotope with 47 protons. And because we need to know the actual percentages of each of these forms, using those percentages, we come up with this number. All right, it's kind of like, I always talk about this in my class, I use weighted averages. 60% of your overall quarter score is your test grade. So it must make sense that your quarter grade is going to be closer to your test grade than your quiz or your lab grade, because the greatest weight of your score is the test grade. Okay, so same idea. So this is what this question is about. All right, so it's 107.868. What they're doing in this question is showing you, or trying to get to this number, even though it may not come out exactly. Okay, so let's get back to the question. To actually do this averaging of the isotopes to come up with some number like this. So we have two isotopes, 107 and 109. Okay, and if you were to do a straight average between these two numbers, you would get 108. Okay, but if you notice, we didn't get 108, we got 107.8 something, okay? So it was closer to 107 because one of the two isotopes exists in a greater abundance. So how do I do this problem? What we do is we find the percentage of each of the atomic masses, and then we add them together. When you do a percentage, you move the decimal place 2 places. So I'm going to move this 1, 2, and so I'm going to take 106.905. I'm going to times it by 0.518, and then I'm going to add it to the next one. I'm going to take 48.2% of this number. So I'm going to take 108.905. That's the actual, okay, very precise mass of that isotope. And you say, why isn't that a whole number? Because protons and neutrons aren't exactly the same mass. We times that by 0.482. Notice I moved the decimal place 2 places. And that's the problem, guys. That's it. Take the percentage of each of the exact atomic masses for that isotope and add them together. So which choice is that? Okay. Notice in choice 1, they forgot to move the decimal place over. Okay. This is supposed to be 0.51. And choice 2 is the same thing, except they're adding the percentages. Okay. Now choice 3, okay, we're still, I'm sorry, for number 2, if it's a percentage, that means it's divided by 100. So again, I get rid of 1 because it's got to be 0.51 here and 0.482 here, so I get rid of 1. This might have looked weird to you, as it did to me when I first saw this choice. Number 3, you can see that just because it's 482, they got 106, so that in number 3, what they're doing is multiplying. They're trying to find the percentage of this isotope, which no, the percentage is due to this one, so that doesn't make any sense. They've got those mixed up. And then they're doing the same thing for number 4. They're putting the wrong number with that atomic mass. So if you think about it, the only choice that makes sense is 2. Now, I'm not a big fan of this question because I haven't quite seen it this way, but it's the only choice that makes sense. What a percentage is a 51.8 divided by 100, right? So by putting a percentage there, they're implying 0.518. And so that's what that is doing there. Okay, not a big fan of the question, but you can tell 1 you cross off, 3 and 4 makes no sense because they were trying to find the percentages of the wrong atomic mass there. So by process of elimination, 2 is the correct answer. The reason why the percentage works here is we have the right number, and a percentage really is moving that decimal place over by saying that. And sometimes they'll give you choices. Well, they'll, instead of moving this decimal place, let me remove it. Let's put the point right here, right? And they'll just take this and they'll have it divided by 100. Okay, so it's another way to see it. So if I was to move this decimal place, get rid of that, and move it back, if you divide by 100, okay, over that entire expression, it's the same thing. And by the way, this right here is a percentage. So again, I think it's easy to eliminate the wrong answer by process elimination, but that's what that percentage means. And this is a very, very, very typical, okay, problem. And you need to understand the wording, okay, because they can say, what is that atomic mass that's listed on the periodic table? And it is the average of the natural occurring isotopes that exist in nature. Okay, so be aware of that wording, okay, as I showed you. All right, so in any case, 32 is 2. On to number 33. Number 33, it's really important to know where you are in this test. So if we're starting in the early 30s here, that's we're doing the B1 section. You should know that this test goes in order of atomic structure. So, you know, here we are with atomic mass number. I'm sorry, a potassium atom has a mass number of 37. What they're telling you is potassium has a mass of 37. That's a particular isotope. Potassium can have different number of neutrons. They're called isotopes, and for the same element. They're just giving you an example of just 37, okay? If we go to the reference table, okay, we need to figure out exactly what the atomic number is to get the neutrons. Remember, what's unique about potassium is its number of protons, which is the atomic number. That's the number, that's the biggest, baddest, boldest number, and it's one without a decimal place. Let's go to the reference table. So there is potassium, number 19 in terms of its atomic number. Now, if you didn't know potassium was K, by the way, if I jump that idea, table S will tell you that. So if you're not sure what the name and chemical symbol is for a name of an element, okay, please go to table S and you would find K for potassium. But in any case, this is the mass number that has a decimal place because it's the what? Weighted average of all the natural occurring isotopes using their relative abundances in nature. We talked about the I think 32, if you got stuck on that question, how that number is a decimal place because they use an average of all the different types and forms of potassium with different number of neutrons. And they average them out using, how much percentages they exist in nature. It's a weighted average. But here, we needed to know the atomic numbers 19. Now, they gave us in the question potassium 37. That's a particular isotope. Notice it's 39 in the reference table. So a lot of people would just say, okay, I know how to get neutrons. I subtract. And if you round this off to 39, which your teacher would do, because that's going to give you what? The most common and the largest abundance in nature isotope. Okay, easy for me to say. 39 minus 19, of course, okay, would give you the 20. All right, but that's not what they're asking. They're asking for 37. Okay, they're asking for the particular isotope of potassium 37. It's still 19 because to be potassium, you have to have 19 protons. Okay, here is the subtraction. All right, so there is what we do there. Now you say, how do I know to subtract to get neutrons? Well, my friends, in chemistry, this number is the mass number. You should know that from table O, okay, neutrons have a mass of 1, no charge. Protons from table O have a mass of 1 and a charge of 1. So these guys have the same mass. So the entire mass of the atom, and if you also look at the beta particle in table O, you'll see that the electron, which is also a beta particle, -1 charge, but they give it a 0 mass. Even though it really does have mass, it's 2,000 times lighter than these guys. So my friends, in chemistry, it doesn't really add to the entire mass of the atom. It doesn't contribute significantly to the mass of the atom. So very simply, entire mass of the atom is due to protons and neutrons. And if you know the 19 protons, and the top number is what? Protons and neutrons, subtracting gives you the neutrons. Okay. So if we do our subtraction, very simple, 17, 8, right? So you're going to get 18 neutrons in this case. But they were talking about potassium 37, not 39. Okay, we needed to go to the reference table if you didn't know the atomic number. Who knows? Unless you're memorizing them on the weekend, and that makes you very cool. Not. Okay, back to the question. So here we are, and it's atomic number 19. And as we said before, okay, do your subtraction, and you're going to get 18. And that's why choice 2 is the answer. Okay, they were very nice because I would think they would have given 20 as a choice here, but they didn't. So it becomes a really easy problem. All right, so on to number 34. Number 34. At room temperature, a student determines the density of a sample of nickel to be 9.79 grams per cubic centimeters. The student determines, that's the experimental value. Based on table S, they're telling you where to go. What is the student's percent error? So I guess we gotta go to a table S and look at the percent error. Okay, now if we're trying to figure out the percent error, we're gonna find out that we're gonna need a known or a theoretical. All right, and that's where they're kind of letting you go to table S there to find that. So what they're not telling you is that there is table T to know what the formula is for percent error. So percent error has a formula. Let's go get that if you have forgotten. You probably have done this in many labs, as my students have also. So let's get that formula first. And again, all formulas for math problems are going to be in table T. That's important that you know it's the last reference table. And let's go there to get percent error if you have forgotten. So there we are with percent error. And we see the measured value, okay, minus the accepted value. So you've got to understand that the measured value is, of course, what the student measured in the experiment. The problem is we've got to get the what? We've got to get the accepted or theoretical value. And they were telling us that table S, okay, has that value. All right, notice we're timesing it by 100 to find a percentage. So we're going to compare what the student found, the measured value, and we're going to need that accepted value. So let's go write down that formula first, and then we'll go to table S to find the known value or the accepted value. Okay, so we've got our formula written down from table T, and we just have to recognize that we're dealing with this measured value, okay, right here. This is our measured value. So let's put that in for measured, right? So let's get rid of the measured, okay, and let's add our 9.79. Okay, now we need the accepted. And if you forgot, table S gives us a bunch of things. Atomic radius, it gives us melting, boiling points, electronegativity, ionization energy, and also gives us density, right? That's what this is found. We're looking for the density value of what? Of nickel. So let's go find that in table S. So table S, as I said, gives you a whole bunch of things, but we're looking for the density. And nickel is right at the bottom here. Atomic number 28, and we're looking for its density, which is 8.90. Again, and that's really all we're doing, looking for that, and of course that is for nickel. Okay, so 8.90 is the known value. That's where they told us to look. Let's put that in our formula. So we're going to put the 8.90 right in for the accepted 8.90. Okay, and we have our equation that we're essentially plugging and chugging. Okay, so no reason to get this wrong. This is a classic either part free response question or a question you see in this part. Okay, so 9.79 minus 8.90, I get 0.89. So I just subtracted these two numbers, and now I'm going to divide by 8.90, so my 0.89 divided by 8.90, I get 0.1, and so this whole expression here is 0.1. I'm going to times it by 100, okay, if you don't see that, and you're going to get 10%. And that's why choice 4 is the answer. So they gave you everything. You just had to know what you were dealing with. They gave you the what? The experimental value, okay, or the measured value from the experiment. You had to look up the known or the accepted from table S, and of course table T gave you the entire equation. On to number 35. Number 35, compared to the metals in period 2, the non-metals in period 2 have what? Ooh, a little tricky. You have to know what these things are. Okay, so let's think about period 2. Period 2, you should recognize that is going to be row 2. So if you're confused about period 2, we're in the second row, or we're n equals 2, and that's given to you actually, okay, in the reference table, the periodic table. So any case, if you look to the left side of that, you can see that, but that's row 2. Now, what elements do we have? Let's draw those, okay? So we have, just write that down here. In the second, we have lithium. We have beryllium. Don't be a boron, okay? Then we've got carbon. Then we've got nitrogen. Then we've got oxygen. Then we've got fluorine, okay? And then we've got neon. Okay, I probably could have done a little bit better in terms of figuring out my spacing, but what do I know? Well, I know that my metals, okay, my metals are going to basically, okay, be on this side. And my nonmetals are on the right-hand side. Now we know there's a staircase, all right? Boron, there's silicon. Okay, if we go a little lower, there's arsenic. Okay, oops, can't see that. All right, so arsenic is there. So there's a staircase. So you should know that your nonmetals, okay, are to the what? Up to the right above the staircase. There's my nonmetals. And then my metals are to the left of the staircase. So you needed to know where they are in the row 2. Okay, so here's a metal. Here's a metal. The nonmetals I'll do in red. because boron is on that staircase, it's a metalloid, along with silicon and arsenic, right? So it's a metalloid, has properties of both. So what they were really saying in this question, compared to the metals, or to the left-hand side, the non-metals, which is the right-hand side, have what's going on here? Okay, well, now that we have established what they're talking about, let me get rid of the staircase here because I want to be able to, write some things here. Let me just white that out. It'll be all white. Don't worry. More bad puns are on its way. Okay, having fun with the puns. Told you. Okay, now, you should know this. Okay, this is atomic number 3. Oh, Christmas, too big. And atomic number 3 is from the reference table. And I put this here because there's some important things you should know. Atomic number 4, 5, 6, 7, 8, 9, and 10. Now, what's so important about these atomic numbers is that this is called the nuclear charge. This is the charge in the nucleus. In the nucleus, you got protons, which are positive. Table O tells you that. Neutrons are there too. Ernest Rutherford in his gold foil experiment said the entire mass of the atom was in a very small space, the atomic nucleus, but the neutrons have no charge. So the entire charge of the nucleus is the proton number. It's also called the nuclear charge. It comes up on tests, so make sure you know the nuclear charge is the proton number. It's not the charge of the atom, it's the charge of the nucleus. Since electrons are not in the nucleus, the charge of the atom, okay, is the number of protons. Now, party people, what happens when you increase the number of protons? Okay, in the same energy level. Because we're in row 2, we're in the second row or the second shell. We're in the same energy shell. Remember, electrons fill certain shells. The first shell holds 2. The second shell holds 8, which is called the octet, which is a stable number. Bottom line is we're in the second row, the second shell. Okay, and we fill that shell with the noble gases. That's why these guys don't bond. But we need to understand something. As we go across, okay, we should know that the atomic radius, okay, starts out big but gets smaller as I go across because the number of what? Protons pulls in the electrons. That's what makes the radius smaller. Okay, so without table S, what happens when you go across period 2? That's what they're really asking, row 2. So compared to the metals, the nonmetals, so the nonmetals are going to have, okay, a smaller atomic radii. We know that. Okay, and because they are small, it's because they have a higher attraction. Attraction for electrons is called electronegativity. You've got to know that. So they have a higher electronegativity because they have a greater number of protons. Even though this question doesn't require everything that I'm explaining, but understanding all of this will help you for other questions that are similar. If I am a smaller radius, that's because I'm pulling in electrons in closer to my nucleus. Why? Because I have more protons. The more protons, the stronger this electrostatic attraction is, and the radius gets smaller. So as there's more protons going across, yes, there's more electrons, but the force of the nucleus in the same shell pulls them in tighter. And therefore, you're going to have a higher attraction. Now, the word for attraction is electronegativity. Now, the other word, ionization energy, everyone forgets. It's the energy needed to pull an electron away. Well, if you're going to pull in electrons closer, hello, you're going to hold on to them tighter. It's going to take more energy to remove them. So what the best answer here is choice 4, higher first ionization energy and higher electronegativity. And that's totally based upon something you should already know, the trends. But wait a minute. If you didn't like anything I did, you know what you could have done? Wait for it. Go to table S. Table S. You could have looked up, not tables, but table S. Okay, you could have looked up every one of these values in row 2 and saw that the ones on the right are going to have a higher electronegativity and a higher ionization energy. Okay, but understanding what I just did will help you navigate similar problems better. So 35 is choice 4, right off table S, but you had to know the non-metals were on the right-hand side of that table, and the metals were on the left-hand side. Okay, so on to 36. Number